Hello, everyone. Welcome to the session on short paper in graph hierarchy and multidimensional. My name is Alfie Abdurrahman. I am from King's College London, and today we have a set of exciting and interesting paper presentation to listen and ask questions about. So our first paper is on combined visual cluster and set analysis by Nikolaus Piccolotto, Markus Wallinger, Silvia Miksch, Markus Bögl, and they are from the TU Wien, Vienna, Austria University. So Markus, the stage is yours.
Thank you for this really nice introduction. So I'm proud to present on combined visual cluster and set analysis. So suppose you are given a multivariate data set. You ask yourself, how can you visually compare if two elements in this data set are similar? You'll probably say, use dimensionality reduction and do a visual analysis of the cluster. But what if this data set also has some categorical columns from which we can derive a set system? You could also add it to the dimensionality reduction algorithm, but then you would lose the specific view of the set visualization. So you would want basically the two perspectives simultaneously, the visual cluster analysis and the set visualization. And some applications require this dual perspective. For example, underground tubes, which I will give a talk about in the session about dimensionality reduction later. And when we developed the underground tubes application, we mostly relied on expert evaluation with domain and design experts, which left some unanswered questions where we thought it requires some controlled experiment. But to understand the experiment we did, I probably briefly have to introduce the underground tube system. So very, very briefly, with underground tubes, we are projecting data points from a high dimensional space to a two-dimensional space. And then to visualize the set relationships, we cover them by lines or trees similar to the metro map metaphor. Probably for this paper, the most important aspect is the first step of the pipeline. So there we have dissimilarities between the elements in the high dimensional space and also the dissimilarities between the elements in the set space. And what we do in this step is we use a mixing parameter alpha to combine them before we project them. So when you have this alpha value set to 0, we only consider the cluster perspective. So in this example here, you could see, if you look a bit closer, that the clusters are kept together, but the lines are fairly complicated. If we go to the other extreme and we just consider the set perspective, then you can see the lines are much simpler, but of course, clusters might be split up. And we can also mix to this parameter to consider both perspectives. So now what we did in the experiment, we used the following data set to generate stimuli. So it was a synthetic data set where each data point had 6 attributes that could range from 0 to 3, which gave us those very simple glyphs. Then for the stimuli, we distributed 6 targets, usually in the stimuli. So those were data points that resulted in exactly the same glyphs, and 36 distractors, which were glyphs that were not similar to the glyph we asked in the task. And of course, we also computed some set system for this data set. And then we had 3 values for alpha. So the cluster focused alpha 0 view, the set focused alpha 1 view, and of course the mixed view where we considered both perspectives equally with alpha 0.5. And the tasks we gave during our experiment were typical visual cluster analysis and set visualization tasks from service. So in T1, we showed the participant a glyph, and then we required them to find exactly the same glyphs in the visualization. With set task T2, we gave them 1 set, and we asked them to count how many data points are actually in the set. And with T3, we did the same with 2 sets, and we asked them to find all data points that are in the intersection. And lastly, we also gave them a joint task. So there we gave the glyph and we required them to find the glyph first, then figure out which set this glyph is a member of and find all other glyphs that are the same and are in the same set. Now, for the hypothesis we had, of course, if you consider a specific perspective, it is probably also the best for the tasks you give. And with the joint task, we conjectured that the cluster perspective would be better just because of the search strategy the participant might apply. And with alpha 0.5, we conjectured that it's never best or worst. So our experiment then, we recruited 49 participants. We performed it as a within subject online survey, and we measured accuracy and response time. We didn't allow the participants any interactions besides highlighting the answer they would want to give. We followed typical study protocols. And in our main experimental part, we showed each participant 24 stimuli, 2 underground tube settings. I will talk a bit more about this later. 3 weights, the alpha 0, 0.5, and 1, and the 4 previously mentioned tasks. Now let's take a look first at the results for the response time. So a bit unsurprising, so you can see the individual tasks and then the alpha value from 0 to 1. Unsurprisingly, if we optimize for a specific perspective, we find a statistically significant difference. If you look at T1, so alpha 0 performs statistically significantly better. The same is true for the set tasks in the reverse. So here the set perspective and the mixed perspective performed considerably better. Unfortunately, for the joint task, we didn't find any statistically significant results. So we can, to some extent, accept the hypothesis about that if we optimize for something, then it will be best. But we had to reject the one that if we consider both weights, would never be best or worst, because this is the case for some data points. If we look at the ranking, this is exactly reflected. And if we look now at the accuracy, here we had a bit more bad luck with our experiments. So with T2, we probably ran into ceiling effects. For T4, we didn't find statistically significant results. And for T1 and T3, we had the expected behavior. So to conclude this talk, a bit unsurprisingly, if we optimize for specific perspective, then of course it also helps us solve the specific tasks. Unfortunately, we had a bit of inconclusive results for the joint task, where we think that because of the text responses we got, that our participants used a different strategy than we anticipated. Now, the core takeaways for the underground tubes application that we had is that we also compared the underground tube systems itself. And here we showed slight difference between trees and paths and what dimensionality reduction we used. So D-grid was better than Hagrid. And overall, if you would only apply one perspective, then alpha 0 would be overall slightly better. But still, I think the main takeaway for us is to really figure out how to make this system so interactive that you can smoothly transition between the alpha values, because this really supports the analysis process, and giving the user the option to change this on the fly is probably very powerful during the analysis process. With that, I thank you for your attention. I'm happy to take any questions now or later in the Discord.
Thank you very much, Markus. So I was going to say, unfortunately, you spoke exactly 9 minutes. So you used up your question time. So
Sorry.
My suggestion is we won't have time to ask you a question, but I actually got your paper and I actually have a question for you, which I'm probably going to actually post it later in Discord or Slido. But please ask the question in Slido and Discord. So our next paper is on an overview plus detail layout for visualizing compound graphs. It is by Chang, Justin, Lieffers, Clayton, Morrison, and Katherine Isaac. So it'll be presented by Chang from Utah University. So Chang, the stage is yours.
Okay, thank you. Share my screen. Okay, can anybody see my screen? Is everything fine? Okay, great. I'll start. Hi, everyone. I'm Chang, a PhD student at the University of Utah. Today, I will talk about an overview plus detail layout for visualizing compound graphs. This is joint work with collaborator at the University of Arizona. Node link diagrams is a prevalent choice for visualizing graph data. The layout can be used to encode additional information. For example, using the edge direction to represent the direction of data flow, and the containment structures to represent compound graphs. An example for visualizing compound graphs is the graph module of TensorBoard. It uses edge bundling technique to maintain stability during interaction, and a bunch of transformations to clearly show the structure. And other famous libraries like Dagger and GraphViz also support compound graphs. One common feature of all these existing layouts is that they use the containments to represent the compound structures, where the child node is put inside the parent node. And like in TensorBoard, the parent node will expand during interaction to contain the child node. We draw an analogy between this approach and the focus plus context view as well as semantic zooming technique, where important details are emphasized, while the surrounding context remains accessible but smaller. In this talk, I will use focus plus context to refer to this type of layout. Just like the focus plus context view, the focus plus context layout also has its limitations. Before expansion, the top-level structure are clearly displayed with a high-quality layout, but the low-level details remain hidden behind the node. After expanding the nodes, the low-level details now become visible, but the high-level structures become distorted and difficult to discern. This reminds us of a technique that is often compared to focus plus context, overview plus detail. We have proposed a new layout for compound graphs based on the overview plus detail metaphor. Here I'll explain how this works. First, let's make a general comparison between these two types of layouts, both fully expanded. At level 0, the overview plus detail layout displays the topology at its most concise form without any expansion, while the focus plus context layout presents the entire graph structure at this level. The same applies to level 1, level 2, and finally at level 3, where everything within this leaf node appears identical in both layouts. The next question is, how should we arrange these overviews and details? That is, how should we lay out the boxes? For this case, the Ringgold-Tilford algorithm works very well, providing exactly what we need. But there is an issue. The box can have varying aspect ratios, and in our application, which we will discuss later, they are often elongated. For example, in this case, we may need to change the layout direction from left-right to top-down. But another node can also be elongated in a different direction. And ultimately, we employ this orthogonal layout, which allows the boxes to be arranged at both directions. Additionally, we also take into account the location of the inner node, the actual overview of the detail box, and position the child node near this inner node, unlike the traditional Ringgold-Tilford algorithm where the child node is simply placed in the middle. Next, I'll go through the algorithm that realizes this overview plus detail design. This is the input data and the result of a standard non-layered Ringgold-Tilford algorithm that we'll compare with. Our algorithm follows a bottom-up approach where the layouts start with the leaf node. In step 1, the two pairs of nodes are arranged left, right, and top down separately, as this minimizes the distance between the overview and the detail. The child box also placed beneath the inner nodes rather than at the center of the parent node, which also contributes to reducing the edge distance. This process is repeated at each step if there is any overlap. After placing the nodes as shown in step 2, an additional separation step is performed to eliminate the overlap. The remove overlap process is equivalent to the problem of finding minimum translation vector, where optimal solutions often require complex algorithms. We opted for a simplified approach with linear running time, performing the separation along both x and y axes twice, and choose the solution that results in the shortest distance moved. In step 3, for example, we separated the two subtrees by moving them along the x-axis. In the resulting layout of our method, the distance between the selected node and its expanded view, i.e. the distance between the overview and its detail, is shorter. This makes it easier to simultaneously explore both the internal details of the group and how that group interacts with its peers at a higher level. And we applied this layout in an application for debugging and understanding a computational network. Our collaborators found it helpful for both understanding the network and locating errors. More details of the system can be found in the paper. Lastly, I want to make it clear that we are not claiming this approach to be a superior substitute for existing methods. Rather, it's an alternative, an option that shows people you can do it this way, and you may consider it. However, to fully understand how people perceive these two types of layouts differently, further empirical studies will be necessary. Okay, thanks for listening.
Sorry. Thank you, Chang. So actually, you kind of we actually, well, I will say we do have 1 minute, and I was going to actually ask the question of in the paper that you were looking at developing, how you evaluated using case studies, and I was going to ask you how you're going to do further evaluation, but you actually answered that by using empirical studies. So okay, cool. So what are your plans for future work?
So I think empirical study also will definitely count, as a future step for this work, because we don't know enough about how people actually differently perceive this. It's we call it overview plus detail, but it's still different than those real overview plus detail layouts that you will see in a map application. Yeah, more studies will be needed.
Okay, cool. Thank you very much. That was a great talk. Okay, so
Thanks.
now we are next to our next paper on improving property graph layout by leveraging attribute similarity for structurally equivalent nodes. And it is by Patrick Mackey, Jacob Miller, Liz Faultersack, and it is being presented by Patrick Mackey from the Pacific Northwest National Lab. So welcome, Patrick.
Hi. Yeah, let me get this started. Here it goes. Can you guys see my slides? Can you hear me? I'm Patrick Mackey, and I'm going to be talking about our algorithm for improving property graph layouts by leveraging attribute similarity for structurally equivalent nodes. So the motivation for this, there's a lot of work into doing graph layouts. One of the many challenges that are associated with them is that users tend to assume that entities in a visualization that are close to each other are more similar to each other than they are the other entities in the visualization that are further apart. So for an example, A user might assume that this orange and this blue node are more similar to each other than they are to the rest of the nodes in the graph. But in fact, all the nodes within this cluster are all structurally equivalent. That is, they all share an identical set of neighbors. In this case, these nodes all share the same single node as a neighbor that connects them all together. So from a graph structural perspective, these two nodes are no more similar to each other than they are any of the other nodes in this cluster. Another challenge, though, is a lot of these real-world networks are actually property graphs. That is, there are properties associated with the nodes and the edges. And in fact, so in this case, these different colors on the nodes represent properties associated with them. And the nodes that are most similar to this orange node are actually these two nodes up here that have identical properties and identical structure. But if we just apply a generic force-directed layout to it, it's not going to take that into account. And the user might mistakenly assume these other nodes are more similar to this one than these ones up here are. So there's a lot of different ways you could try to solve this problem. There's existing algorithms out there, for instance, that take both the structure and properties into account, and they use both of those as a part of an equation to move the nodes around so that both are taken into account. But what we wanted to do was really be able to take a classic graph layout that was focused primarily on structure, so whether it's force-directed layout or any of these other existing layouts, and then simply just swap the locations of the structurally equivalent nodes so that we're not moving them around so much as just swapping them so that the ones that are more similar to each other in their properties are closer to each other in the final layout, which you can see in this example here. Some common structurally equivalent node patterns are some of the following. These are ones that we see a lot in some of the real-world data we have been working with. One example is the fan-out nodes. That's that example we showed at the beginning where you have a single node attached to a lot of other nodes that's the only node that they are connected to. But other common patterns include things like connector nodes, which can connect to two different nodes, or also singletons. So like when you see a lot of nodes that have no edges at all, that can happen in certain types of graphs. And then lastly, another pattern we sometimes see in some of our data are these complete bipartite graphs or connected components, where you have two sets of nodes that are all connected to each other. So how do we find these structurally equivalent groups of nodes, or SEGs as they're sometimes called? Well, it ends up there's actually a really simple algorithm for doing this, and it works in linear time with respect to the number of edges in the graph. The way it works is you simply, for each vertex in the graph, you look at all the neighboring vertices, and you take the hash codes associated with those neighboring vertices, and you combine them together with an XOR operation. And this will provide you a new hash code for that node based entirely on its neighboring nodes. And since structurally equivalent nodes all share the exact same set of neighbors, it means all the structurally equivalent nodes will end up having the exact same hash code. And that allows us to then collect all those together, and then we have our structurally equivalent groups. So once you have your structural equivalent groups, you then have to also have some sort of scheme for sorting these nodes by their similarity. And there's actually a lot of different possible techniques for this. So we have one that worked well for our needs, so we present that in the paper, and it's the following. So given a set of node locations from your initial layout for a group of structurally equivalent nodes, we first apply principal component analysis to find a line that captures the most variance among the group of those locations within that group. Once we have that line, we simply order those node locations based on their location along that line. So that gives us our location ordering. Once we do that, we can also do something similar, ordering nodes based on their properties. So for this, there's many different approaches you could do. So some things like numerical data, it's very straightforward. For things like categorical data, there's other approaches you can do. And we go into this into some more detail in our paper. But again, this is something where you could plug in different approaches if something would work better for your needs. And then lastly, once you have a ordering for the node locations and you have an ordering of your nodes based on their property similarities, you then simply have to map the node to the location in a one-to-one mapping based on those two orders. And you get your final layout like you can see here, and now our nodes have this nice smooth gradient in their properties. So next, I just want to give some examples of what this looks like for certain types of structural equivalence groups you might see in real-world graphs. So for our first example here, this is kind of a pattern we see a lot in our data, which is the high degree fan out. We have a single node attached to many, many different nodes, and you get this kind of dandelion effect. And if you just apply generic force-directed layout without taking the properties into account, you get just kind of a random sprinkling of these nodes. It can cause a lot of confusion for the users as far as which nodes are more similar to each other. Applying our technique, you get this nice smooth transition from left to right with the nodes based on their properties. And it becomes much more easier for the user to kind of get a sense of where the other similar nodes are, as well as get kind of a sense of how many nodes there are of different values. This example is using categorical data. So the color represents something like, say, node type associated with the nodes. And in this case, we have many different types of structural equivalence groupings. But even within this much more complicated graph, you can see how that rearrangement really helps allow the user to see where those similar nodes are and just kind of get a better overall sense of how many nodes there are of the different types. And then lastly, we wanted to bring it back around to that original example we showed at the beginning. This graph is actually one where we have multiple categorical properties we're looking at, which is why you see multiple colors associated with some of these nodes. And using our ordering approach for that, we see that we now finally have the orange nodes all together, just like we originally had hoped. And so hopefully this allows the user to get a much better sense of what they're looking at and where the similarities actually lie in the graph. And with that, I just want to thank you for your time and also give special thanks to our sponsors from the Department of Homeland Security who helped us do this research. And with that, I can answer any questions you might have.
Thank you, Patrick. I think we may have enough time to squeeze in one question. We don't have any question from the Slido, so this is a question for me. So could you possibly describe what potential future work, what's the next step that you're going to do from here?
Yeah. So we are currently integrating this into a software package that's being used by a number of different folks and basically kind of trying to explore how people want to use this. So for instance, we talked about in the paper how you can combine multiple properties together. And so you can sort them by a lot of different properties, but our data has a lot of properties. And one of the things that we think might be the case is they might actually want to just do it based on one property at a time, so that allowing the user to basically select which property is currently driving that additional adjustment to the layout. So for maybe one particular use case, they're mostly really interested in this one property, and so allowing them to look at that at a time. Otherwise, if you combine too many properties together, I think the similarity kind of gets washed out, and it's maybe not as useful. So that's something we want to study a little bit more.
Okay, thank you very much. Thank you for the nice presentation. So I would say a big round of applause in Discord. So thank you. So we shall go to our next paper presentation. The title of the paper is Fields, Bridges, and Foundation, How Researchers Browse Citation Network Visualization. And the authors are Kiroong Choe, Eunhye Kim, Sangwon Park, Jinwook Seo, and it is presented by Jiru Chu from Seoul National University. So welcome, Jiru. Kiru. Yeah.
Okay, thank you for introduction. I'm Kiroong Choe from Seoul National University. I'll present my research on browsing citation networks. When searching for research papers, we often look at citations. And using list-based interfaces like Google Scholar, we click on links like related articles or cited by to view each fragment in separate lists. This method is suitable for viewing direct citations or references, but it is hard to understand more diverse or deeper relationships at the same time. And it is well known that network visualizations can show these relationships intuitively. However, it is also well known that network visualizations can quickly become complicated. When we are dealing with citation networks, the complexity is actually greater than you might have thought. In this image, the red node is in the center is one of my papers, and other points are some of its direct references or citations. When we show the citations among those neighboring papers, it's not that unreadable but it is already too complex to use as some intuitive tools for understanding or browsing citations. But this is the case for my paper. And if I put my professor's paper instead, it becomes practically impossible to understand. Remember, this only shows the one seed paper and its direct neighbors. So regarding citation networks, it is even challenging to play with 1 degree of separation from the seed paper. So the applications using citation networks, like connected papers, do not actually show the complete citation network. Instead, they select some nodes and edges based on their system criteria. In such systems, the control over navigating the network are with the system and not for the user, which limits users from engaging with the network for further curiosity. We wondered how people could take a more active role in navigating citation network. And if it is difficult to understand due to scalability issues, even at the most basic level, then it is very natural to think about simplifying the nodes and edges in some way. Indeed, various studies related to network simplification have shown promises. For example, Dune's work shows that the graph on the left can be simplified as shown on the right. However, existing studies on network simplification are mainly about general network and not about academic browsing. So the simplification targets are often structures like stars, cliques, or chains, but it's unclear how these components are meaningful in academic context. And also it is unclear what users need from the citation network in the first place. So our research questions are as follows. When browsing citation networks, what structures naturally capture their interest? Do these structures enhance? That is, do these structures actually help the search process? To answer this question, we conducted an empirical study. We had 18 HCI and social science researchers engage in 2 days of individual browsing of citation network, and we collected a total of 179 post-assessment records to analyze patterns from. Let me briefly explain our task. This is the interface that our participants used over the 2 days. On the interface, users could specify some seed papers, and the system displayed the citation network around those seed papers. We asked the participants to freely explore the network, find interesting papers in the network, and then fill out a post-assessment form about them. The post-assessment form was structured like this. It displayed a screenshot of the network when the user found the paper, and they annotated and described why it was interesting for them. And we asked the users to read more about the paper and classify whether it was actually helpful for their research with a yes or no question and provide reasons for that. For the sake of time, I'll briefly introduce the important findings. About the first research question, what structures naturally capture their interest? We found 6 major patterns as shown in the figure. These patterns were divided into 2 distinct perspectives. First, in the layout-oriented perspective, they tried to understand the network's overall shape rather than each individual connection. On the other hand, in the connection-oriented perspective, users analyzed each connection to form some kind of conclusion in bottom-up way. Within each perspective, there were 3 components: fills, bridges, and foundations. And roughly speaking, users wanted to find something clustered in the network and related them to research topics in the academic context. They also wanted to find something connecting, which corresponded to research novelty, and they wanted to find something sequential, which represented research trends. These results show what users were interested in, but it doesn't tell us if it was actually the case and useful for their research. Especially the layout-oriented perspective itself might be questionable, since in citation networks, the citations are the main thing and the layout is just a byproduct. This leads to our answer to the second research question. Do these structures actually help the search process? According to our statistical analysis of the post-assessment records, papers found through layouts were actually less useful than those found through connections. Nevertheless, participants preferred the layout-oriented perspective. This was because thinking based on the layout made it much easier to form a framework for interpretation. However, when such expectations diverged from the actual data, they felt frustration. They wanted the network layout to be clearer, such as having explicit access. So our results show implication for future systems. To meet the user needs for seeing underlying topics, interconnection of topics, and research trends in the network, the layout should be well designed to display these effectively. Also, the layout should be as clear as possible. And for example, for the idea of using axes on the network, we find Schneiderman's work quite inspiring for future system design. Okay, thank you very much for listening, and please feel free to ask questions.
Hi, thank you so much for the presentation. So, I think this might be a question from you from Slido. So the question is, during the studies, were there any differences in results depending on the participants' expertise?
Yeah, that's a great question.
Because was it 18 people or 21 people you
Yes, 18 people.
evaluated with?
Empirically, I didn't find that much correlation from the expertise, but there was actually difference in their perspectives or preference. So there were some people who didn't like to assess the citation relationship at all, and to someone who very believed in the citations. So that kind of differences were very evident. But yeah, for the expertise, I think further research is needed.
Okay. Thank you, Kiroong. And so I think further question can be asked on Discord. So we will be going to our next paper on feature clock, high-dimensional effects in two-dimensional plots. And the authors are Olga, Ovcharenko, Rita, Sevastjanova, Valentina, Boeva, and it is presented by Olga. So welcome, Olga.
Hi, can you hear me and see the slides? Great, just a second. So hi, I'm Olga, master student at ETH Zurich, and today I'm going to tell you about feature clock, a visualization tool to show high-dimensional effects in two-dimensional plots. So let's start with motivation. High-dimensional data is difficult to perceive, and we normally use dimensionality reduction techniques to visualize data in 2D and later analyze. And a common and simple approach that probably everyone knows is linear dimensionality reduction. In essence, linear dimensionality reduction techniques find a transformation matrix that is W. And if we multiply W with original high-dimensional data, we get a low-dimensional representation. And an example of linear dimensionality reduction is PCA. Linear dimensionality reduction techniques are easy, fast, and explainable, and there are dedicated plot types, such as biplot, to visualize feature contributions or so-called feature loadings to analyze low-dimensional space. Feature loadings are the vectors showing individual features changes, and on the slide you can see a biplot for a very popular iris dataset that contains 3 classes of flowers and 4 features that characterize each flower. So unfortunately, linear dimensionality reduction is not always able to capture the underlying data structure, and therefore we use nonlinear dimensionality reduction. But there is a question on how to interpret low-dimensional space produced by nonlinear dimensionality reduction and how high-dimensional features influence the latent space. So it's difficult to analyze how gradients move on a manifold because the movement is nonlinear, and additionally there exists no transformation matrix W, and therefore no biplot with feature loadings. And therefore a common visualization and what people commonly do is find in low-dimensional space, let's say with UMAP or TSNE, and then creating a scatter plot for each feature, color coding points by feature values, as shown on the slide. This allows users to analyze each feature in the low-dimensional space, but this solution is not scalable because it requires k plots for k features. And there is an open question on how to depict high-dimensional data trends in two-dimensional plot and how to interpret low-dimensional space after non-linear dimensionality reduction. What we suggest is a feature clock, a single plot that can explain low-dimensional space after the linear or non-linear dimensionality reduction, and it can even be used to explain neural networks. Here you can see a feature clock for t-SNES space for, again, iris dataset. Now, how feature clock is built. First, we apply any dimensionality reduction technique to our data, which we call X, our high-dimensional data, and we call our low-dimensional data Y, and let's say we applied UMAP to X. We need to decide how to measure feature importance, and we employ linear regression between high and low dimensional data. Linear regression produces coefficients for each feature, and we use them as feature importance. So now we are interested not only in the coefficients, but also in the direction of the biggest coefficient to make something like biplot for linear dimensionality reduction. Imagine we want to calculate how all features change in the direction of some angle theta, and what we can do is project low-dimensional data y onto the line at angle theta and then calculate coefficients of linear regression and fit linear regression. This means that for each feature, we should find an angle at which the coefficient is the biggest, and a naive approach is to iterate through all possible angles between 0 and 180 and calculate coefficients. But we found a faster analytical solution. To get an exact solution, we fit just two linear regressions between high-dimensional data and low-dimensional data that is projected on X and Y axis. So this corresponds to brown and blue arrows on the slide. And after we use simple Pythagoras theorem to find the biggest coefficient of each original feature and its angle. It is a very simple solution, and it fits just two linear regressions and uses Pythagoras theorem, and we get all largest coefficients, and we can see how our features change in nonlinear space. The final step, though, is filtering out coefficients that are statistically insignificant. For each coefficient, we perform t-test and use p-values to find the probability that coefficient is 0 and does not influence the linear model. So we do not visualize statistically insignificant coefficients since they do not contribute to our linear model. This is the whole method. And now I will talk a bit about design choices. So to explore low-dimensional space, at a finer granularity, we suggest three versions of a feature clock: global, local, and intergroup. Global clock gives a general trend, but can miss some information. Local clock shows feature importances at finer granularity for classes or some clusters, or uses selected points. And intergroup clock shows how points change between classes or clusters and explains how to move a point from one class to another. Yeah, now use cases. Because of time constraints, I will present only one use case on data analysis. And on the slide, you can see feature clocks for the support dataset. This dataset comprises information on critically ill patients across US medical centers. And each patient is assigned one of 9 diseases. And on the slide, on plots, each point is a patient, and there are 2 classes of patients who survived or didn't survive in a hospital. There are 46 features in this dataset in total describing each patient, and feature clock allows visualization of top K most significant features. For support dataset, we visualize top 4, the most significant features for each clock. The global clock shows that disease class, this is blue arrow, cost charges ratio, this is orange arrow, and average t-score, this is brown arrow, and Apache 3 score, purple arrow, differentiates the outcome of critically ill patients. So we see that patients with a less severe disease class survive more often, and medical centers charge these patients less. We also see, so what is t-score? The average t-score is an estimate of the severity of disease, and Apache 3 score is an early warning of or indication of death, and most of the diseased patients had both scores, high both scores. So now local clocks. Local clocks represent points that belong to either the survival or death class, and we can see how features changed within each class. And I will not stop on local clocks because of the time, but if you're interested, you can look at the paper and see what drives each class. Now, intergroup clock shows features that differ between diseased and living patients, and mortality increases with higher values of the average T-score, which is brown, do not resuscitate order day, which is light brown, and if resuscitation was given, this is darker green. So negative outcome is more likely if there was something connected to resuscitation. And interestingly, number of days in study, this is turquoise, also influences the outcome. The less days patients spent in hospital, the more likely patient is to survive. So don't go to hospitals. Now, to summarize, we suggest an open source library and technique called feature clock. Feature clock is scalable and compact technique that enhances explainability and can be used with any dimensionality reduction technique, and it can be even used to explain neural networks. And in future, we plan to rethink how to use nonlinear methods to estimate movement on manifold. And additionally, we consider making feature clock more interactive with the lasso 2 and GPU accelerator. That's all. Thank you.
Okay, thank you, Olga. So I do have a question. So my question is, one of your use cases is the one in the hospital, and then the other one is a diabetic case, isn't it?
Yeah.
And the question that I was going to actually ask is that you did an informal evaluation using, is it students from ETH? So
Yeah.
how does that actually map in a way? Do you evaluate it using the data sets, the medical data sets? Do you need to train the participants to recognize certain things?
We have basically shown scatterplots to the participants and asked to explore the dataset using scatterplots, and then we suggested feature clock, and we also asked our participants if it was easier to understand the dataset and analyze dataset with a feature clock.
Okay, cool. So unfortunately, we just slightly over a minute, so that's fine. But thank you, Olga. And I suggest to the rest of the audience, please go to Discord and ask the speakers question about their work. So our next paper is on uniform sample distribution in scatterplots via sector-based transformation. And the authors are Hennes, Rita, Valdemar, Molchavno, Lars Linson, and it is presented by Hennes Rita from University of Munster. Yeah, welcome, Hennes.
Yeah, thank you for the introduction. Can you hear me and see my slides? Okay, so hi everyone, I'm Hennes from the University of Münster in Germany, and I will be presenting our paper, Uniform Sample Distribution in Scatterplots via Sector-Based Transformation. So in our paper, we present an algorithm that transforms a scatterplot such that the samples are more evenly distributed. The transformation is smooth and no mixing occurs, which means that the neighborhood of samples as well as cluster boundaries are preserved. Why would you want to do this? One reason is to reduce clutter. It is also much easier to estimate the sizes of clusters. For example, the yellow cluster has twice as many points as the blue one, which is very difficult to estimate in the original scatterplot. Also, when you're using glyphs or small images for each point, our method can reduce overplotting. But I want to be clear, in most cases, our method is not supposed to replace the original scatterplot. Instead, we think it's best used in conjunction. A number of approaches have been proposed to reduce clutter in scatterplots, all with different kinds of drawbacks. Our approach generalizes previous work from myself and my co-authors, so I want to give you a brief introduction. If you want to know more details, be sure to visit my other talk tomorrow in the full paper session on embeddings and document spatialization. Essentially, in our previous paper, we divide the domain into 8 regions, 4 of them axis-aligned and 4 tilted by 45 degrees. We do this for each point in the scatterplot. We then compute the density of points inside each of these regions using integral images. Afterwards, we move points away from overpopulated and toward underpopulated regions. And then we asked ourselves a very simple question, why just these 8 regions? So in this short paper, we generalized the previous integral image-based approach to an arbitrary number of regions. Here's how it works. First, we split the domain into sectors. Again, we do this for each point in the scatterplot. In this example, we chose 16 sectors, and they are shown for the point at the edge of the yellow cluster. We then count the number of points in each sector and compare this to the sector's area. This tells us whether a sector is over or underpopulated. Here, 3 sectors are strongly overpopulated, as indicated by the red color. Also note how the sector which contains the right side of the orange cluster is underpopulated, even though there seem to be quite a few points inside it. This is simply because the sector's area is quite large. Each sector is assigned an anchor point, which lies on the domain boundary on the opposite side. We find the anchor point by computing the intersection of the sector's angle bisector and the domain boundary. Our deformation is then just a linear combination of all anchor points, weighted by the difference between the expected and the actual density inside the corresponding sector. So in the end, we get one deformation vector for each sample in our scatter plot. When we perform this transformation iteratively on all points, we approach a uniform distribution of samples in our scatter plot. If we look at the sector colors, we can see that the expected and the actual density inside each sector move closer and closer with an increasing number of iterations. We can also see that no mixing occurs and the original neighborhoods of each point as well as cluster boundaries are preserved. This iterative nature of our algorithm makes us believe that it lends itself well to an interactive analysis, where the user goes back and forth between the original and the decluttered layout. I also wanted to show you a real-world example. This is a UMAP embedding of the iris dataset, where it takes only a few iterations until there's no more overplotting. Also, there are 3 orange points inside the blue cluster, which were hidden in the original scatter plot, but are clearly visible after just one iteration of our algorithm. To evaluate our approach, we computed several quality metrics which measure the uniformity of the scatter plot, as well as the preservation of the ordering and local neighborhoods of points. You can see the details in our paper. For this talk, however, I want to focus on one metric in particular. When we look at this example, we can see that the scatter plot produced by the new approach looks more uniform. Each sample seems to have more free space surrounding it on average. To quantify this, we came up with a quality metric, which we call sparsity. To compute it, we determined the minimum of the distance to the closest boundary and half the distance to the nearest neighbor for each sample. We then fit a regular hexagon around each sample, and importantly, we know that no other point lies within this hexagon. We then just divide the sum of the areas of all hexagons by the area of the domain. This value lies between 0 and 1, and it approaches 1 when the scatter plot is perfectly uniform and the hexagons fill the entire domain. This metric is also independent of the number of samples in the scatter plot, as opposed to, for example, taking the average distance to the nearest neighbor. We computed the sparsity for roughly 3,000 real-world datasets and saw that our approach significantly outperforms the previous one in almost all cases. Additionally, we wanted to investigate the choice of parameters. So we analyzed the effect of the number of sectors on the sparsity. Interestingly, we saw that increasing the number of sectors is more effective the fewer points we have in our scatter plot. This makes intuitive sense, since a higher number of sectors increases the angular resolution. And when there aren't many points in the scatter plot, it is especially important to be able to tell exactly where they lie relative to each other. So to summarize, I presented our approach for decluttering scatter plots, which works by dividing the domain into sectors and iteratively moving samples away from overpopulated and toward underpopulated regions. We were able to show that we achieve better results when compared to the previous integral image-based approach. However, there are also some remaining topics for future work. First, we would like to improve the performance of our algorithm. One idea would be finding a data structure that lets us efficiently count the number of samples in each sector, as opposed to looking at each pair of points individually, as we're currently doing. We also want to integrate our approach into a visual analytics tool to see how it can support actual visual analytics tasks. And finally, we would like to come up with a heuristic for choosing the optimal parameter setting. This will likely depend on the dataset size. This concludes my talk. Thank you for your attention, and I'm happy to take your questions.
Thank you for the talk. So let me see whether there's any question from Slido. I can't see, but let me ask a question. So you mentioned in your presentation that the algorithm is done using number of using iteration. So what is the stopping criteria? Is there a stopping criteria to find an optimal spacing between the points?
So in an interactive setting, when our algorithm is used in an interactive setting, the user would typically decide when to stop. But if you want to use it fully automatically, you could use one of the quality measures that we defined and specify a tolerance or a threshold, for example. Another option would be looking at the actual deformation vectors for each point. So when the magnitude vanishes, so basically nothing is moving anymore, that would probably also be a good stopping point for our algorithm.
Okay, thank you very much. So I think there's a reminder that you have another presentation. Is it tomorrow?
Yeah, tomorrow.
Yeah,
Also in the
okay.
first
So
session.
you might want to put it in Discord so people could come and join and follow on from the work for tomorrow's paper. So thank you very much, Hennes.
Thank you.
Okay, so we are to our next paper, which is called Ghost UMAP, Measuring Pointwise Instability in Dimensionality Reduction. And the authors are Wong Jung, Takanori Fujiwara, Jiaminjo, and it is presented by Wong Jung from Sungkyu Kwan University, Korea. Welcome. Are you muted?
Thank you for the introduction. Could you see my presentation? Thank you. Hello, everyone. I'm Myungwon Jung from Interactive Data Computing Lab of Sangwon University. Today, I'm going to present our research titled Ghost UMAP, measuring pointwise instability in dimensionality reduction. This work is a collaboration with Takanori Fujiwara from Linköping University and my academic advisor, Professor Jae-min-jo from Sangwon University. UMAP is one of the most widely used dimensionality reduction techniques due to its good performance. UMAP computes the two-dimensional projections of high-dimensional data, which can be visualized as a scatter plot. However, UMAP has a limitation that the results can vary with each run. For example, the inner cluster structure can be changed globally in different runs. In addition, we noticed that many points fall into different clusters across different runs, which we call local instability. The local instability poses a significant issue, making it challenging to interpret the results consistently. There are two main reasons for the local instability. First, UMAP generates a different starting projection for each run. This can be alleviated by using a fixed number to generate consistent starting projections or by initializing with PCA. Second, random negative sampling is used to reduce the computational cost. While increasing the sample size could reduce randomness, but it is impractical due to the high computational cost. To address this issue, we introduced Ghost UMAP, a novel technique designed to identify locally unstable points caused by randomness within a single run. The core concept of Ghost UMAP is to introduce clone data points referred to as ghosts. These ghost points represent possible locations computed with different negative samples. In addition, by computing multiple points for an instance and using the variance between these points as a measure of instability, we can easily distinguish between stable and unstable instances. This is the result of Ghost UMAP. The star symbol represents the starting position of each point, while the cross and triangle symbols represent the final locations of the original and ghost projections, respectively. On the left, the original and ghost points converge to the same location, indicating low instability. On the right, the original and ghost points are separated into two distinct groups, indicating high instability. Before discussing Ghost UMAP, let me briefly introduce UMAP. UMAP has two main phases. First, in graph construction, it transforms high-dimensional data into a topological representation, reflecting the relationship between data points in high-dimensional space. In the layout optimization phase, UMAP simulates both attractive and repulsive forces between points using the topological representation to optimize the lower dimensional projection. The difference between the standard UMAP and the ghost UMAP lies in the layout optimization phase. At the start of this phase, the original projection is initialized. In ghost UMAP, the ghost projections are generated by simply copying the initial original projection and ghost times. After that, the original and ghost projections are optimized separately. This table shows how the attractive and repulsive forces are applied to the original and ghost points. For the original point, both forces are applied exactly the same way as in the standard UMAP. As a result, the original projection is identical to the result of a standard UMAP. However, the forces applied to the ghost points are newly defined. The key point is that the attractive and repulsive forces for the ghost points are not calculated based on other ghost points. Instead, they are applied with respect to the points in the original projection. For the original point, the attractive force is always calculated based on its neighbors in the high-dimensional space, which is the fixed set of points. Also, for the ghost points, the attractive force is calculated using the same set in the original projection that was applied to the original point. For the repulsive force, the original point calculates it based on negative samples. However, for ghost points, unlike the attractive force, the repulsive force is computed using a different set of negative samples, which are drawn from the original projection. This approach allows the ghost point to simulate the possible alternative positions that the original point might appear in different UMAP runs. We qualitatively evaluated ghost UMAP using the MNIST dataset with 16 ghost points per instance. On the left, the original point belongs to the red cluster of digit 2, but 6 of its ghosts are projected to the blue cluster of digit 0. To understand why this occurred, we examined the image of the original point, which shows an ambiguous handwritten digit 0. Indeed, each neighbor in the high-dimensional space consisted of classes of digit 0 and 2. These neighbors could diverge the attraction forces and make the projection more sensitive to negative sampling. Therefore, each point position may result from randomness and should be interpreted with caution. In conclusion, ghost UMAP provides an effective method for capturing the randomness present in UMAP projections. Additionally, it allows us to quantify point-wise instability, making it easier to identify unstable points within the projections. It also highlights the need for caution when interpreting results, as UMAP's non-deterministic nature can introduce distortions. That wraps up the presentation. Thank you for your attention.
Thank you for the great presentation. So I don't think there's any question on Slido. So let me ask a question. So the question is, so you use ghost UMAP. So how does ghost UMAP manage the increased computational time that is being introduced by the additional of ghost points?
Thank you for the great question. Yeah, the way how we manage the increased computation time is to adopt successive halving technique. Successive halving works by calculating the instability of each point at certain iterations and then removing the most stable half of the ghost point. It allows us to focus only on the most unstable ones and reduce computation time by up to 45% while maintaining high accuracy.
Okay, that's great. I would say thank you very much. And we are now moving on to our last paper of this session, which is going to be given by Mark Keller. And the paper's title is Use Coordination, model, grammar, and library for implementation of coordinated multiple views. And the authors are Mark Keller, Trevor Mans, Neil Gilles Lebons. So our presenter is Mark. So Mark, welcome.
Thank you.
Okay.
I'm presenting here at Boston Viz, this use coordination work. And we know that visual analytic systems often employ coordinated multiple views. So you might think this is a solved problem. And in a sense, it is. There are many theoretical models for coordination in the information visualization literature. But then the next question you might ask would be, are there any software implementations? And there are, but a lot of these were published with the initial theoretical models and are therefore obsolete. So another obstacle here is that a lot of these implementations use event-based mechanisms, which are not very natural in the modern user interface development frameworks that are popular today. There are sometimes assumptions about data being tabular, which we know is not always the case. You might have, of course, images or networks that you want to coordinate. Sometimes there's coordinated multiple views implemented within a visualization framework, but this presents challenges when you want to coordinate across different frameworks. And often a visual analytics system developer might implement their own coordinated multiple views setup, but this can be redundant. So our goal here was to develop a more declarative approach that could coordinate across frameworks and languages, for example, and would be compatible with reactive user interface development frameworks or paradigms. And we want to consider coordinated multiple views separate from the implementation of a visualization itself, or separate from data structures or how views are laid out. And we also want to be able to coordinate any type of value, so not only like primitive numbers and strings, but more complicated arrays or objects. And of course, we want to develop something that is documented and open source and easy to reuse. And we don't necessarily need to reinvent the theoretical models, as these already exist. So what we present is a model and grammar and a software library for implementation of coordinated multiple views. And so, as I mentioned, this might traditionally be implemented within a particular visualization framework, but our approach lifts the coordinated multiple views part up into the app level. We base our model on the existing abstract model for coordination and extend it with certain concepts, but the main concepts here are borrowed from that approach, which are the views, a coordination space, which contains coordination types. And these are the named properties that you'd like to coordinate, like zoom level, for example. And then within a coordination type, there are these instances called coordination scopes. So if your application has two separate zoom level values, then those can be linked to two different sets of views, for example. And this is a more concrete example. We see here these 4 scatter plots where all 4 have the same zoom level, but the top row is the overview, has this overview offset value of 0, so these are zoomed out, while the bottom row of detail scatter plots has this zoom offset of 2, which makes them more zoomed in. Meanwhile, the left column is the UMAP dimensionality reduction points, which are coordinated to one center position, so this target position, which effectively results in linked pan interactions, while on the right column, these have an independent center position, resulting in a separate set of pan interactions. And we see this here in this, this animation. The zoom levels are linked, but the left column has separate pan interactions from the right column. And so we extend this also, we show that this declarative approach lends itself to extensions like this editor, this visual editor that you see here in the bottom right. So using that flow-based diagram, we can dynamically change which scatter plots are coordinated together. So we can, for example, set all of the pan interactions to be linked together. We can also have another extension, which is to export the specification to GraphViz. We have a Python implementation, so it's not only JavaScript, it's more general, but we provide an object-oriented API to more easily manipulate the grammar. And you can also use the declarative nature to implement things like provenance tracking, undo, redo based on this, this grammar. And as we show, we implement this in a React hook function called use coordination in this library that we provide. And I'll just demonstrate this quickly. So in these bar plots, we have a bar plot, the same bar plot implemented with 4 different visualization frameworks here: Bögl, D3, VIS, and Plotly. And these have a bar selection property that are all coordinated. But we can show if we want the bottom row to be coordinated to a second, selection value, we can do that in our editor here, and we see those are separately coordinated now. We show here, you can do this for other types of visualizations, like, medical imaging volume, and we can have a scatterplot matrix. Each of these scatterplots is coordinated with their brushing being done via this coordination space. And in a more contrived example, what if every other scatterplot is implemented with a different framework here? So every other one is Plotly, and then the alternating plots are D3. So here we show you can coordinate those. And to finish, coordination is not a solved problem, but our library can simplify this implementation. And I'd like to acknowledge our lab at Harvard Medical School, the reviewers, and the organizers. So thank you.
I am muted. So thank you, Mark, for the great presentation. So obviously, I noticed there's software that people can download and use. So my question would be well, actually, I have 2 questions. So probably the first question is, what kind of evaluation have you done or testing that you have done on your approach? And then the next question is, what's next? What's the plan
Thank you
for the
for the
future for this?
question. Yeah, so the evaluation, we haven't done any type of user evaluation. I think that's an area where we can do follow-up work. I think this we've been using this internally, so we of course it works for our use cases, building, for example, by interactive visualizations of biomedical data, including complex multiplex imaging data, where you might want to coordinate the colors of a certain image channel across different images, for example. But then for what's next, I think there's a lot of room to be done for the visualization of the coordination. So helping users to understand which properties are coordinated in different visualizations. I think that's a hard problem that deserves a lot of attention. So thank you.
Okay, thank you very much. So I believe we have reached to the end of our speakers. So I'd like to say thank you very much to all our speakers that are here for presenting their work, and thank you for the audience for listening. Please ask questions on Discord. And I also would like to thank the student volunteers and the technicians. So we're going to have a break for about half an hour. Then there are plenty of sessions that we could go. I think there's about 2, 4, 6 parallel sessions. But in the meantime, let's give a round of applause to our speakers, student volunteers, and technicians. Please ask questions on Discord. So thank you, and please enjoy your coffee break, and see you in the next session. Thank you. Bye-bye.